So this is a topic that a lot of people might have heard about. In fact, it's in a lot of school textbooks, but usually it would be referred to the case of Galileo, for example, who was, let's say, it would have been said that he was persecuted for his belief that the sun was at the center of the universe. And this was something that was quite controversial at the time. There's a whole history around it, and I was going to take you through some of that history and what actually happened, and what was the church's position, what is the church's position now, what actually happened in all of this. And it's a very interesting subject. It's got a lot of details, and some of it might be a little confusing. So I will present everything, and at the end, if you have any questions, I'm happy to elaborate on anything and go into details if you're interested about anything in particular. About me, I'm not a full-time academic. I've got a degree in theoretical physics, and I've got a postgraduate diploma in science and religion. And I work full-time as a software engineer, which I've worked in transport, cartography, and nautical navigation. And in my spare time, because I have so much of it, now I've got 3 kids, I translate the works of Riccioli, particularly the Almagestum Novum, which is a work from 1651. That was the most comprehensive textbook of the time, and it's never been translated to English. In fact, few people have ever read it because it was so long. The book's about this big, they're about this thick, and written in a minute script with hardly any punctuation. So few people actually braved the whole thing, even in the original Latin. But it's full of really interesting subjects, full of really interesting annotations about what was happening at the time. So it's an absolutely fascinating work. The first volume is available for purchase. I'll be selling it at a discount afterwards if anyone's actually interested in pursuing this a bit further. So I think before we dive into the whole debate, we have to go through a bit of the history, but before what's happened with Galileo and all of that. And the first thing to think about is about ancient cosmologies, ancient astronomy, what was happening there. So the Ptolemaic model on the right is probably what you might be familiar with. That people used to think the Earth was at the center, that all the planets went around the Earth, including the sun and the moon. And people would refer to the sun and moon as planets as well. Planets was just any star that was moving in the sky. It wasn't with the rest of the stars in a fixed position. On the left, things you might not know so well, a model of Plato and Eudoxus. So they had something called a homocentric ring system. And these are all rings at the same distance, and they can actually create this retrograde motion. So when Mars, for example, goes back in the sky, because usually all the planets travel in one direction, and sometimes Mars goes in the other way. And that's called retrograde motion. And actually, Eudoxus' model could model that. But after Ptolemy, his model was entirely accepted, and it was pretty much the standard for over 1,400 years. Now, there were some other alternatives. The earliest thing that we have similar to a heliocentric model, so a heliocentric is when the sun is at the center, was the Philalaic model on the left here. But it wasn't actually the sun at the center. He had a central fire. And this was something that was behind the Earth. This was to explain why you had, for example, volcanoes with fire coming out from underneath. What was that all about? So he postulated there was a central fire around which the Earth orbited. And the sun orbited this as well. And he also believed that there must be an anti-Earth, something that was on the other side of the sun, like an Earth, to balance out the Earth. There was a lot of thinking around balancing. There's also something called, a lot of thought in the ancient times about something called the antipodes. And this was the idea that there should be land on the other side of the Earth balancing out the Middle East and the European, the Asiatic lands on this side. So they actually postulated there might be something like an Australia on the other side of the world, without ever having been there. And then we have Aristarchus of Samos, who did actually suggest that the sun was at the center of the world, but we know very little about it. None of his work survived. And the only thing we have is this little quote from Archimedes. He says, his hypotheses are that the fixed stars and the sun remain unmoved, that the Earth revolves about the sun on the circumference of a circle, the sun lying in the middle of the orbit, and that the sphere of the fixed star, situated about the same center as the sun, is so great that the circle in which he supposes the Earth to revolve bears such a proportion to the distance of the fixed stars as the center of the sphere bears to its surface. So that's all we know about Aristarchus. So people had heard about such an idea, but it was quickly abandoned after Ptolemy. So now let's go back to the Ptolemaic model. Now, it wasn't simple circles. What we actually had in the Ptolemaic model was a deferent, which was a single circle, and then epicycles, which follow this particular point around the inside deferent. This was to model some of the movement, and this is how they modeled the retrograde motion of Mars and so on. And most planets had an epicycle. Some had a few. Cosmologies that were either Pythagorean or Platonic or Aristotelian. They believed in the 4 or 5 elements. And this all tied into a wider cosmology where they thought that the Earth was made of earth and it drew everything in. The celestial objects were made of ether and they couldn't be drawn in. They were just following perfect circles, which was a perfect shape. There are only 2 types of perfect movements, either straight movement or circular movement. And circular was considered the more perfect because it was closed. It just kept going into eternity. Straight movement was a bit problematic in that sense because it had to have a start. Because if you couldn't get to a middle point, because it wasn't countable, that's how they imagined infinity. So it was impossible for it to be a straight movement. It had to be circular if it was to be perfect. So we also have something called the eccentric and equant. And the eccentric was actually the center of the orbit. It wasn't the Earth. The planets didn't exactly orbit the Earth. The Earth was a bit off-center. This explained why planets sometimes seem a bit bigger or smaller, or sometimes brighter or dimmer. And the equant was a point on the other side of the eccentric, around which planets moved at a similar pace. Now, this was a big problem for Aristotelian and Platonic cosmologists, because everything should have been following in perfect circles, and this slowing and speeding up of the planets around the points was very problematic for them. So here's a brief animation that more or less shows the Ptolemaic model. You can see that you have some of these patterns that emerge, and this was quite for a lot of people, this was persuasive of how amazing the universe was, that there were these beautiful patterns. It was very mathematical and geometrical, and people really liked that. What we'll find later is a lot of these patterns come from the fact that the planets have certain times at which they appear next to each other again and again, and that's where some of the similar points end up together, and that's why you have the little spins, the little loops. Now, epicycles are very interesting. Now, you can actually model any shape with epicycles so long as it's a closed loop. So there's a website somewhere which actually lets you draw anything, and here's an example of a dinosaur drawn with epicycles. And a lot of people thought that what had happened was Ptolemaic astronomers had been always adding more and more epicycles to make things more accurate, but that's actually not true. There were 34 spheres or epicycles in Ptolemy's original model, and there were 34 around the time of Copernicus as well. This myth started from a few discovery of a few documents of King Alfonso X, stating that if he had been God, he would have made the universe a bit simpler because of how complicated the model was. Copernicus, in his Commentariolus, which he released in 1514, he said that he could build his heliocentric model with just 34 spheres, which sounds like he was comparing it to something else. Amusingly, he actually miscounted the amount of spheres in his own work, and he'd actually done it in 38. And the last one is a misreading of Fracastoro's Homocentrica, which was an attempt to bring back, if you recall, the Platonic and Eudoxian astronomical model with the rings kind of on the hinges. And he used 80 spheres, but he was not using a Ptolemaic model. And people misread that for a while and thought that Ptolemaic astronomers had been using 80 spheres, and that just frankly wasn't true. And so enter Copernicus. This is a painting by Jan Matejko. Now, I don't know if you can spot an error with this painting. Anyone? So this was a mistake. This was actually an early sketch, and what's in there is a telescope. Copernicus did not have a telescope. Telescopes weren't invented for another 70 years. So he was made aware of this, and he removed it, and you can see he's got slightly older instruments there, but you can see his model on the bottom left. So anyway, Copernicus was born in 1473. And he built this model, which might seem familiar. So the sun at the center, circles going around it with the planets, with the Earth, with the moon going around the Earth. And a lot of people think, oh, this is a lot simpler than all those epicycles and all of that complicated stuff with Ptolemy. But people don't know that actually the real Copernican model used more epicycles than the Ptolemaic model did. He used 38 spheres in the Commentariolus, which he released in 1514. But by 1543, when he released his De Revolutionibus, he had actually added another 10, and he used 48 spheres. Part of that was adding the Tusi couple. So he was actually doing something that was unusual in that he was solving the problems of Aristotelian cosmology, where there was the equant and there was a lack of circular movements. And he added more circular movements to make it more perfect from a cosmological perspective. And in that way, he added more circles, and he put the sun at the center, but it wasn't a simpler model. It was a more complicated model. And another myth that people often think is true is that that perhaps Copernicus was persecuted in his lifetime, or that he might have released his book just on the verge of his death, because the Revolutionibus was released the same year that he died. And neither of these are true. He'd started the publishing process earlier. He'd released his Commentariolus a lot earlier. Everyone knew he was a follower of the heliocentric model. And he didn't really have any issues with the church or with anyone in his own lifetime. In fact, Pope Clement VII approved his model in 1533. He organized a lecture in the Vatican, and he rewarded the man who gave the lecture. And Cardinal Schönberg offered, he was a leading cardinal. He was very important up in the hierarchy. He sent a letter to Copernicus saying, "I'll give you some money if you send me an advance copy. I'd really like to see this ahead of you publishing it, so we can stay up to date and all of that." And Copernicus put that in his book as well, in the foreword. And his own bishop was supportive, as well as Bishop Gies, who was his lifetime friend, and he actually was the one to persuade him to publish his book. So there was clearly no issue at the time. And in fact, we find that the Jesuits were the ones who spread Copernicanism across the whole world, to the point that actually the first ban of Copernicanism was in Japan under the Tokugawa shogunate. They banned it in 1613 as a wider ban against Christianity. They saw Christianity as a threat, and they sought to ban everything that Christianity had brought there. Okay, so while the Jesuits were spreading the Copernican model, it wasn't seen as a realist picture of the universe. They didn't believe in it as a cosmology. They saw it like they'd seen the Ptolemaic model as a mathematical tool. It was a hypothesis, an idea, something that could be used mathematically to get the positions of the planets. And that's how they saw it, really. People did start getting persuaded by it, and Copernicus himself clearly believed in it. But people didn't know that either, because in Copernicus's preface to his book, Osiander, his publisher, had added a statement that it should be treated as a mathematical model. And this caused a lot of trouble later down the road. I'll try and come back to that later. But by the end of the 16th century and by the start of the 17th, what had grown was a Tychonic model, which was proposed by Tycho Brahe. Now, this was essentially the Copernican model, but seen from the perspective of the Earth. It used the same mathematics. It had the same relative positions of all the planets to the Earth as the Copernican model did. And Tycho Brahe was incredibly persuasive. He was incredibly well regarded. He ran an observatory comparable in cost and scale to NASA today. And he wrote to almost everyone in Europe worth writing to, all the astronomers, all the rich people. He was an aristocrat himself, something unusual. Aristocrats didn't usually get involved in astronomy so much. And what you can see in his model, well, you probably can't see it quite there, but in the middle was the Earth, and the Sun orbits the Earth, and then the other planets orbit the Sun, which seems unnecessarily complex, but it solved a variety of problems. It solved the problem of why should we think the Earth should be moving. No one thought the Earth was moving, really, at the time. It was more aligned with Aristotelian cosmology in that the Earth was at the center. It explained why we didn't feel the Earth moving. This is a big problem. The Earth, in Copernicus' model, would be traveling at thousands of miles an hour. And no one felt this. No one felt the spin of the Earth either. Why would we not feel that? You know, if you're traveling on a horse, you definitely feel it. And Copernicus' model should have also meant that there should be a measurable stellar parallax. Now, stellar parallax is this idea that if you look from one eye and then from the other, you might see that some things shift a bit to left and right behind each other. Now, with Copernicus' model, over a year between summer and winter, you should be able to start seeing some parallax between the stars. And this was not observed. And this was a problem for the Copernicans. If there was no stellar parallax, then there was no evidence that the Earth moved. In fact, this was the only experiment to differentiate between heliocentrism and geocentrism up until 1651. This was a damning proof that heliocentrism couldn't be right. The Copernican model was considered slightly more complex, and this is a bit ironic as well. The scientists of the time thought that the Earth in Copernicus' model needed an extra sphere to explain why, despite it moving, it was always aligned to the same polar position in the sky. And this was because they didn't understand the gyroscopic effect. So because the Earth spins, if you've ever seen a gyroscopic top, no matter if you hit it, if you poke it, it always stays upright. And that's more or less why the Earth remains aligned most of the time. But they didn't understand this back then. So after Tycho, the next big guy was Kepler. And Kepler came up with the three laws. He came up with the idea that planets move along ellipses around the sun, or with the sun at a focal point, to be precise. It's not at the center either. And he figured out that a planet travels with equal areas over the same period of time if you take a segment of that ellipse. So he figured out exactly why, or rather how, planetary movements are as they are. And this was an incredibly accurate model. It was the most accurate model of the time. But there were some problems with it. Now, this picture on the right presents his actual model. People know about the three laws, but they don't know that actually Kepler, his model was quite, I would say, occult. It was quite weird in the sense that it was mathematically beautiful, but it relied on a variety of ideas. The ideas of Platonic solids being the determinant for why there were certain distances between the planets. He thought there were 5 planets. There are 5 Platonic solids, so it seems to all make sense. And he also brought in the idea of musical harmonies, that there should be a particular harmony between the distances between planets. And he tied music into it. And I would say it was very mathematically beautiful. I wouldn't say it was simpler than any of the models before it, though. But it did provide a constraint, because while epicycles can model any ellipse, having ellipses meant that the amount of possible movements of the planets was constrained. So it was a better scientific model in that sense. And it could model the path of comets, while epicycles could not, because comets do not necessarily form closed loops. Some comets fly into the solar system, and then they fly right out. They're not necessarily in an orbit around the sun. They follow something called a hyperbolic trajectory. So then we have Galileo Galilei. Now, people are often confused. Why does Galileo come after Kepler? Didn't Galileo pursue Copernicus's model? And he did, that's right. And the fact is he ignored Kepler's model entirely. Despite it being the best model of the time, Galileo considered it a cult. He rejected much of what Kepler wrote. And in fact, we don't know too much exactly why he didn't pursue it, or whether he had read it, in fact. We do have some notions of him rejecting Kepler's ideas, such as the fact that he rejected Kepler's model of the tides because he considered it a cult. But Galileo had a number of observations that you might know about: the phases of Venus, Jupiter's moons, Saturn's companion stars, sunspots, and lunar mountains. And a lot of people think, well, Galileo, he proved that the sun was at the center. But it's not actually true. What they did do is they discredited Aristotelian cosmology, the idea that celestial objects were perfect. The sun was clearly not perfect. It had sunspots. The moon was not perfect. It had mountains, and they were lit from the side. You could see the shadows move. If you look for a telescope, you can see this really well. You can see the shadows move behind the mountains, so you can see exactly how it's lit. It's reflected the light. It's not coming from the moon itself. And it discredited the Ptolemaic model because the Ptolemaic model didn't account for the phases of Venus. But the Tychonic model did account for the phases of Venus because it had the same mathematical formula as the Copernican model. The Tychonic model did account for the phases of Venus and for all the other observations as well. And Galileo's other arguments that he presented through his life were also not very persuasive either. For example, one of his main arguments was his tide theory, which he claimed showed that the heliocentric model was right, but it did not, in fact. He, in fact, rejected the idea that the moon could affect the tides in any way, which was phenomenal because people had known for thousands of years that the moon caused the tides. In fact, I've studied a variety of medieval tide diagrams that are actually pretty accurate. They have little circles, they have the lunar phase, they have the lunar position, and they predict the tides pretty well. Galileo rejected this, and any sailor would have probably, laughed his pants off seeing what he'd written. And so what happened with Galileo? So Galileo, he was a witty chap. He used to cause a lot of trouble. He argued a lot with people. Some of the people he argued with were the Aristotelian scholars that he nicknamed the Pigeon League. And they obviously didn't like him very much because of what he wrote about them. He often made fun of them. And he wrote a long letter called the Letter to Castelli, and then expanded to the letter to the Duchess Caterina. And in it, he criticized them heavily. And the other thing he did was he interpreted scripture, saying that all scripture could actually be understood better if you looked at it from a heliocentric perspective. Now, the Aristotelian scholars, the Pigeon League, thought, well, we're going to catch him here. What we're going to do is we're going to take him to court over this. And they took him to the Inquisitorial Court, which was a high court in the Papal States. And they complained about this. They said, look, he's interpreting scripture. He's not a theologian. He's getting it all wrong. And clearly scripture says that actually the earth is the center. And there's just, I think it's one major reading, the reading in Joshua, where the sun stopped in the sky. And they suggested that this showed that the sun was moving. Galileo interpreted this as, well, actually, it'll be much easier if the earth stopped its spinning than for the sun to stop moving. Surely that would be easier. Galileo himself believed that at scripture and science, there was no conflict at all. His opponents did not believe that. And the interesting thing here is that it was the standard in the Catholic Church that if science and scripture disagreed, and the science was clear, then science should take precedence. This was the case in Augustine and in Aquinas, who both wrote as much. But what was the case was the fact that Galileo had not proved that heliocentrism was true. And the Inquisition consulted astronomers, and the astronomers were still overwhelmingly supporting the Tychonic model. And so they said, well, no, Galileo's wrong. The heliocentrism is not right. And the Inquisition said, well, if the science isn't proved, then we can't accept this interpretation of Scripture as Galileo would like to have it. And what they did was they gave Galileo an injunction, a court order. They said, you must not claim that heliocentrism is true or interpret Scripture based on it, unless you can prove it. And you can't. That's what they told him. And they also modified Copernicus's book to make it clearer that it was a hypothesis. Now, what they thought they were doing is they thought they were legalizing what was in the preface of Copernicus's book. As I mentioned, this was written by Osiander, his publisher, who had added it when he had published it. And they thought that Copernicus had actually written that it should be treated as a mathematical tool. And the Inquisition said, this is what should happen. This is what astronomers should say. They should say, this is a mathematical tool if they're writing about the heliocentric theory, unless they could prove it. And they banned a work of Foscarini, who was another man who at the time of Galileo had also tried to interpret Scripture based on heliocentrism. Now, people were a bit obviously perturbed by this, and Galileo in particular. But when the Pope changed in 1623, this was a few popes on, to be fair, but Urban VIII had actually been someone called Maffeo Barberini, and he had actually supported Galileo when the Inquisition had first investigated him in 1615. He had defended Galileo, not because he was a heliocentrist, but because he was something called an instrumentalist. He didn't believe that scientific observation could necessarily prove one thing or another, that those kinds of questions would always be left to philosophy ultimately. But Galileo thought with Urban VIII, he's got a chance to maybe push heliocentric theory again. And Galileo went and consulted Urban VIII, Pope Urban VIII, 6 times on his new book, the Dialogue on the Two World Systems. But he didn't tell Urban VIII about his court order and his injunction that he'd been given not to publish a work claiming that Copernicanism or heliocentrism was true. And after he had consulted the Pope, he modified the book further to make it more heliocentric against the Pope's wishes. Then he found a way to get around the imprimatur system, so this was a system to check whether books were okay to write, whether they were accurate. It was essentially a peer review system. And he published it. And this was a huge embarrassment for the Pope, because it turned out he'd written a pro-heliocentric book against a court order he'd been given by a high court. And the Pope had been involved. He'd been an accessory to the whole thing. So this was a great embarrassment to the Pope, who had many rivals. A few years later, in fact, there was an assassination attempt of the Pope. So there was a lot of turmoil at the time. And the Pope did not need any more embarrassment or issues. So there was a great anger in the Vatican, not just from the Pope either. The Inquisition were obviously upset that their court order had been breached. And they were also, in a way, happy to be able to attack the Pope and the Master of the Sacred Palace, who they saw as political rivals in the church hierarchy. So there was quite a bit of politics around it. And in 1633, Galileo was condemned. He was put under house arrest for the rest of his life. It wasn't a dreadful house arrest in the sense that he actually had freedom to walk around. He had astronomical gear he could use there to study astronomy further. He had servants, so he was better off than most people were under lockdown. But on the other hand, it was a very severe punishment for something that we wouldn't consider punishing these days. At the time, there was no idea of freedom of speech. So it's a bit difficult to try and look back on it from today's perspective and see what was right or wrong. But it was certainly an excessive punishment, and we can see that from the fact that various people pleaded to the Pope for pardons, including the Polish king, including the French ambassador, who all thought this was actually dreadful and unprecedented, frankly. People were surprised by it, for sure. So following Galileo, this is where Giovanni Battista Riccioli comes in, and this is the man whose works I'm translating. And in 1651, he wrote the Almagestan Novum, and in 1665 he wrote his Astronomia Reformata, and in it he actually included Kepler's laws in a geocentric model, like a Tychonic model. And this was, at the time, an even better model than what had preceded it. So people were not persuaded by Galileo, and the consensus was still for the Tychonic model for quite a while. You can see here, this is from the frontispiece of the Almagestan Novum. Riccioli presents the heliocentric on the left model and the Tychonic model on the right. And they're weighed. They're saying whose evidence is heavier, weightier. And he says the Tychonic model is far heavier. It's got the evidence behind it. Now, why is that? So we already know about the lack of stellar parallax. And Riccioli also came up with the idea of the Coriolis effect. The idea that on a spinning Earth, things shouldn't go in a straight line if they're traveling, because you're on a spinning Earth, and as the Earth spins, you start sliding a bit to the side. In the northern hemisphere, the Coriolis effect pulls you a bit to the right. And this has a variety of effects. Snipers in the army often calculate the Coriolis effect to try and account for it when they're shooting. Meteorologists know that the Coriolis effect causes cyclones and in above the oceans. So it's a well-known effect. But what happened was Riccioli said, if the Earth's spinning, this should be measured. And he tried to measure it, and it couldn't be measured. Now, we know from later on that it was just too minute of an effect for him to measure, but he wasn't aware of that. He just said this should be an effect. He showed that it should be, and he showed that it couldn't be measured. So there were two things that couldn't be measured at the time. And out of 126 arguments he presented for and against heliocentrism, he said, these are the two proofs that the Earth is neither moving nor spinning. And this was the case up until Newton. Newton brought his classical model, mechanics. It had the idea of forces, and the forces explained why Kepler's model was right. If there is an inverse square law of gravity, then planets have to travel in an elliptical orbit around the sun. And to be more precise, around the barycenter, which is a center of mass, a center of gravity between any two objects. And for most objects, apart from Jupiter in our solar system, that barycenter is within the sun. But there were many benefits of Newton's model. One was that it worked both locally and in the heavens, in that you could test it by throwing a ball, and you could test it by measuring the position of the stars. It was hugely successful. And it was after Newton that people started being convinced of heliocentrism. This is when the scientific consensus changed in astronomy. People were convinced heliocentrism, it must be true. And the fascinating thing about this is that it was the mathematical model that changed, and there was still no direct empirical evidence of heliocentrism at the time. The first heliocentric empirical evidence was Bradley's aberration. This came in 1727, so almost a century after Galileo's works. So with Bradley aberration, he was actually trying to measure stellar parallax, but he couldn't measure it. But what he found is that the position of stars changes slightly depending on whether you're going towards them or away from them. And you could see this in the sky when depending on which way the Earth was going around the sun, different stars moved a bit more towards towards the Earth, and some moved away if we were going away from them. This was the first empirical evidence of heliocentrism. And then more came later. So the next one was the equatorial bulge, which was predicted by Newton, but it had actually been tried to measure numerous times, and people had various measurements. So Cassini, a famous astronomer, thought that the Earth was kind of rugby ball shaped, and he found measurements to suggest that. But in 1736, there were more accurate measurements made by Le Condamine, and then a few other astronomers showed that actually there was an equatorial bulge, and this was proving that the Earth was spinning. Because if the Earth spun, then there should be, the middle bit should kind of bulge out to kind of account for that. You know, when you're going around a corner in a car and you get swayed a bit to the side, this is why the middle of the Earth, the equator, should bulge. Then stellar parallax was measured finally in 1833 by Friedrich Bessel. And finally, Foucault's pendulum in 1851, here with the animation. This was a pendulum that spinning round. So a pendulum just left freely oscillating, it would slowly spin round. And that's a bit sped up, because actually what it does is it spins round in 24 hours. And what it shows is that there is a Coriolis effect. This is actually the first time that the Coriolis effect was demonstrated in a laboratory, was in 1851 with Foucault's pendulum. And this was actually after Coriolis. Coriolis came earlier. Coriolis, like Riccioli or like Euler, he had just provided a mathematical model. He hadn't actually seen it. Foucault was the first. So what about the church? What happened with the church? Now, the church and the Inquisition had really stopped being interested in the whole affair by the start of the 18th century, because people were convinced by Newton by the end of the 17th century. It had become a dead letter law. So you might have heard of some of the laws in England, for example, where we're supposed to, all the men should be practicing archery on a Sunday. These are the kinds of laws that we still have, but we don't follow. And this was the same with the Inquisition. They still had Copernicism on the index, but frankly, they weren't adding any new works. They weren't really bothered by people following it. But people were kind of still noticing it, and it was upsetting people that it was still there on the index, especially for very faithful Catholics who might have been looking at the index and following it. They, would have not been happy about it. So the Inquisition changed their stance officially a number of times. So first in 1744, they allowed Galileo's Opera Omnia, so his full works, to be published by under the editorship of Giuseppe Taldo. Then Copernicism was removed from the index as a general rule in 1758. And then in 1820, we had quite the opposite case of the Galileo affair. What happened there was Setele, he had written a heliocentric work, and the master of the Sacred Palace at the time, he had refused to publish it. He had said, well, actually, I'm not convinced heliocentrism is true yet. So there were still some people, they were a minority, but they still thought that the Earth was at the center. Now, the Inquisition took up this case, and they forced the master of the Sacred Palace to publish this work. So it was quite the opposite. And as a result of that case, they changed two things. In 1822, they gave express permission to publish any works advocating Earth's motion. And in 1835, they removed Galileo's and Copernicus' works explicitly from the index. Now, these hadn't been removed in 1758 as a kind of legal complexity, in that the Inquisition did not have the power to remove things from the index if they had been added by a trial. So it was only once the Giuseppe Setele case had happened that they could remove these things from the index legally. Now, the funny thing was that heliocentrism didn't turn out to be true either. What we discovered over time is that the solar system travels around the Milky Way, and there turned out to be more galaxies that were far away, and Hubble discovered, they were moving faster and faster away. And we also had Einstein's general relativity. So it turned out that the whole affair, the whole debate between geo and heliocentrism was frankly a bit silly. None of them turned out to be right. There's certainly been quite a bit of controversy around it, but they all turned out to be wrong. And this is one of the great ironies of the history of science, and there's so many ironies. As we saw, Galileo didn't have proof in his time. He turned out to be kind of right. You know, it turned out to be true that the Earth moves, that it spins, but he had provided bad methodology. He'd got the tide theory wrong. He'd thought he had proved something when he hadn't. And then you have the opposite. Riccioli, who had thought the Earth doesn't move, and he'd predicted the Coriolis effect, and he thought that showed that the Earth doesn't move, when actually it turns out that the Coriolis effect is one of the great proofs that the Earth does spin. So there's a lot of irony involved. Anyway, let's move on to what happened later in terms of the church. Now, Pope Leo's Providentissimus Deus, I think that's 1867, I think. In it, he actually accepted the theology of Galileo. Galileo's theology was actually pretty good. People have criticized him for being a bad theologian, but it's not true. He followed the standards set by Augustine and by Aquinas, and there was nothing wrong, frankly, with what he wrote. Now, John Paul II issued the first statement on Galileo in his Einstein Centennial speech in 1979, where he stated that there was wrongdoing by organisms of the church, which seemed like an admission that the church had done something wrong. So while the Inquisition had changed its stature, they never apologized, they never admitted they'd done something wrong. And this is an interesting problem, because wrong and right is kind of hard to understand from a historical perspective. There are different standards of different times. Can we look at the past from our current perspective and say someone in the past was wrong? And there's different ways of interpreting that legally or morally or kind of objectively. Anyway, the Pope John Paul II then started an investigation in 1980, and he didn't seem to endorse the full conclusions either. He did have a speech in 1992 at the Pontifical Academy of Sciences, which some of you might remember, because in the media there was a portrayal that the Pope had apologized for how Galileo had been treated. And it's kind of partially true. If you read his speech, it suggests that that's what he's saying, but a lot of people weren't satisfied by what he had said. He didn't give him a full rehabilitation. It was not a formal statement. He didn't say it ex cathedra. He made an informal statement where he hadn't accepted the full results of the 1980 investigation. So it's interesting. And there were problems with the 1980 investigation. It lacked some details. It didn't involve some of the top scholars of the Galileo affair. So there's a whole bunch of complexities we could add there. But certainly John Paul II admitted that there were problems and that the church had treated Galileo badly. And that seemed to be the extent of it. Now, there are some new developments right now. Most of you probably won't know about this, but there is a neo-geocentric movement. These are people who look at the theory of general relativity and they say, well, in general relativity, everything's relative. So perhaps that means that the Earth could be at the center, since all the science works in that way anyway. But this is a very small minority. It's some members of the Colby Center, which is in America, and they think that the world universe might be geocentric. But this is definitely not an official position of the church. The church's position is probably better exemplified by the works of the Vatican Observatory, who are, in full accord with standard science of the time. And the other development is that there are new translations of early modern texts. I'm working on some of them of Riccioli. There's also works by Christopher Graney, who works with the Vatican Observatory. He's translated the works of Loca, Ngoli, and other scholars who show a very different perspective on the Galileo affair, particularly around the science of the time, which turns out to be not aligned with what Galileo was saying at all. It's quite fascinating because a lot of what people learn in school is still about the Galileo affair, and what's written in textbooks is still a lot of myths that were created by Enlightenment authors in the 1800s. And a lot of it is wrong. And historians didn't start discovering this till the 1960s when they started re-examining the works of Galileo. So there's still a lot being discovered even now because works have not been translated into contemporary languages until now. So that's pretty much it. I've got some recommendations if anyone wants to read further. A really good book or two really good books on the Galileo affair would be Finocchiaro's Galileo affair and Retrying Galileo. The Retrying Galileo is a good book that covers all the myths and where they came from around the affair. And then there's early modern science books such as Graney's Setting Aside All Authority, which shows why science was opposed to Galileo at the time. And my own Alma Gestum Novum goes into that as well. So that's it. And if you have any questions, I'm happy to answer them now. I hope that wasn't too much to take in. But
it's the 1992 thing. Oh, the church only got round very, very late in 1992 to actually accept, the Galileo's ideas and whatnot. And it's used as another condemnation of the church.
Yeah. So this is it's worth knowing about the 1700s and what happened under the Inquisition. And so people often criticize the church for not accepting heliocentrism until 1992, which is kind of amusing because heliocentrism was no longer considered true at that point. But certainly the Inquisition had made official moves to make heliocentrism accepted as early as 1744. And even by then, they weren't really enforcing any of the rules. In fact, they hadn't been enforcing the rules particularly well earlier. So here on the right is a map. It's from a survey by Owen Gingerich. I'm not sure how to say his name. But he made a survey of all the copies of Copernicus's texts. And what he found is the little black dots are where the censor of 1616 was enforced. The white ones are where they weren't. And you'll see that most of Europe, it wasn't enforced at all. In the Papal States, it was partially enforced. And in fact, the Roman Inquisition had added Galileo to their index, but the Spanish Inquisition, for example, they never added Galileo to their index because they considered the 1633 index to be anti-Spanish, because it contained some Spanish works on it. So there was a lot more complexity to the whole case, for sure. Yeah.
So what are our grandchildren being taught in science now?
So this is definitely a problem. I've my brother-in-law is a teacher. I looked at his physics textbook, and I found errors on Galileo the moment I opened it. It is a problem. Most people don't know the real story. Even if they do, they might claim, well, the simplified version's all right. And it usually says something along the lines of, oh, Galileo proved the heliocentric model and he was condemned for it. And frankly, neither of those claims are true. I would say it's important for teachers to know this and to present it, because it's frankly ridiculous that something so anti-Catholic could be in school textbooks, right? Yes?
Could you say a little bit more in layperson's language about the Foucault's pendulum and the Coriolis effect? Coriolis, what does that mean? Did you say that was someone's name? Coriolis?
So yes. So this is a bit confusing because the Coriolis effect is named after Coriolis, who was a French physicist in the 1700s, and he neither suggested the Coriolis effect, nor did he demonstrate it, nor was he the first to make a mathematical model of it. And somehow he's acquired the effect has his name. And so with it's quite difficult to do with just speech, but it's if you have a merry-go-round, for example, and if you threw a ball to someone else on the merry-go-round, it would seem quite normal if you look at it from outside of the merry-go-round. It would seem like the ball traveled along a straight path and everything was normal. But if you're on the merry-go-round and you see it from that perspective, the ball looks like it's turning. And this is exactly the effect that should occur on the Earth if it's spinning, and it does, and we know it does. The faster an object moves, in fact, the more it turns a bit, and it turns to the right in the northern hemisphere, to the left in the southern. It's some people claim that this is why you see water spinning into your bowl in your sink one way or the other way in Australia, but that's not actually true. That depends more on the various inconsistencies in your actual sink. But it is a cause of cyclones. So the funny thing is, cyclones actually go anti-clockwise in the northern hemisphere, which confuses people. They think, oh well, that means the Coriolis effect moves left. But actually, what happens is you have something called a balance between the pressure gradient and the Coriolis effect. Now, the pressure gradient pulls air into a pressure center. If it's low pressure, they're dragged in. And this is balanced by the Coriolis effect. So as the particles try and come in, they're shifted to the right. And they continually go round and round instead of being drawn in by themselves into the pressure gradient. And the fact is, because the Coriolis effect depends on the speed, as it goes faster, the Coriolis effect is stronger. That means if they try and go faster, they swerve more to the right. And that's why you get the cyclones. Yeah, exactly.
And that's why the pendulum doesn't go like this.
Yes. But the effect is so small that until you have your pendulum running for 24 hours, you wouldn't notice it. Yeah.
Have you been interested in this for a long time? And were you sort of from school? Were you very interested in this or not? Come later.
So in my postgraduate diploma, I studied the Galileo affair in detail. But actually, my more recent interest started when my friend, who is an astronomer, he gave me his old telescope, and I started looking at the stars and the planets and the moon through my telescope, and I was interested in why the moon has lots of craters named after Jesuits, and actually my favorite author, Giovanni Battista Riccioli, he is the man who named the craters on the moon, and he was a Jesuit priest. And he named all the lunar craters. He made a beautiful map of the moon. He named all of the craters after all the famous Jesuit priests who had been astronomers before him. And it's kind of interesting as well how he named them. You might, if you ever have a study of the moon, the most prominent craters are probably the Tycho crater. This is a big crater that seems to have these long lines coming out from it. And that's because Riccioli was convinced by the Tychonic model the most. The second most prominent crater is probably the Copernican crater. Really stands out. So clearly Riccioli was influenced by Copernicus. And the third one is Clavius, which is a really beautiful crater. It looks really nice for a telescope. And Clavius was the Jesuit priest who reformed the Jesuit academia to include a lot of mathematics and astronomy. And Clavius taught Riccioli, and that's why he's a very prominent crater on the moon as well. And interestingly, Galileo was what Riccioli thought was a crater, but it turned out that Riccioli had thought it was a crater, but it turned out to be just a prominence in the sky. So later on, different people moved the Galileo lunar crater naming to a different place where it was actually a crater. So, yeah. Yes? At the back, yes.
Argument between geocentrism and heliocentrism purely a European issue, or do you find similar things in Indian, Chinese, Arabic astronomy and clashes with religion?
Really good question. So the question is this just a European debate? Did this happen anywhere else? Now, I know some of my Muslim friends would claim that there are some ancient Muslim texts that claimed heliocentrism was true. But I'm not convinced any of them were as successful as what was happening under Copernicus and onwards in Europe. In India, we have a guy called Nilakantha Somayaji, for example, who made something like the Tychonic model years before Tycho Brahe did. So there was some, I think in India, there was certainly some debate around these kinds of discussions, but it was certainly only parts of India. Now, when Jesuit missionaries came to Asia, to parts of India, there were parts of India, particularly some of the Buddhist parts, that still believed in a flat Earth. Now, flat Earth hadn't been believed in Europe since antiquity, but it was not the case out in the Far East. The same in China, there were still some flat Earth models. They weren't exactly flat. They called them the bamboo hat models. And in Japan, this was new. And something that I recall reading was that the Chinese and the Japanese were often surprised when the Jesuits brought up the debate of geocentrism and heliocentrism, because they didn't see why they should care about it at all. It wasn't something that they thought was problematic. But certainly the Jesuit missionaries did the great work of spreading modern astronomies across the whole world. And the funniest thing is that our calendar is Catholic. It's a Gregorian calendar. And amusingly, the Chinese calendar was formulated by Jesuit priests. So there are two leading calendars that were created by Catholics. And in China and Japan, there was decent astronomy going on, but it was mostly to do with the calendar system. For example, in China, calendars were reformed every time there was a new emperor. And if an emperor didn't reform the calendar, he was considered weak. He was in charge of everything, so he should form a new calendar with new ways of doing things every time. Yes, does that answer your question? Yeah. Yes.
Do you think the idea that someone might even work, etc., that in earlier times upset the church, in as much as, God in charge of everything? Was it a kind of threat?
So the question is, was an understanding of the heavens, of the planets, considered a threat by the church? Yes. So I wouldn't say that. The power, or whether it was a questioning of the power of the church. Now, I wouldn't say that was the case. Frankly, the church stayed out of astronomy in academia for most of the history. There were a few interesting things, such as there was a long time persecution of astrology, but this was actually split. They split the idea of astrology into judicial astrology and natural astrology. Now, judicial astrology was the kind of horoscope making, predicting that empires might fall, that someone might break their leg going downstairs in a few days, or anything like that. This was condemned. Whereas natural astrology was the idea that the stars had an effect on medicine, on the weather, on the tides and things like that, and that was actually okay. So it was fine to do natural astrology, and people are a bit surprised, but medical astrology lasted until probably the start of the 19th century. So it's very recent that we got rid of astrology in medicine. So there was a condemnation of astrology. In terms of astronomy, I think there are, so people claim that Bruno was killed for believing in the heliocentric model, but there's actually no evidence for that. His condemnation states only his denial of transubstantiation. I'm not saying his burning at the stake was nice. It was obviously horrible, absolutely horrible, but it wasn't for scientific reasons. Now, there is perhaps some second or third hand evidence to suggest that people did consider his belief that there were other planets with other people on them to be a heresy. But frankly, that would have been a very minor heresy amongst all the other things he said, because he followed pretty much all the heresies of the time, or even more of them. He was in fact considered a heretic by the Protestant groups of the time as well. So Giordano Bruno, yes. So he didn't believe in the divinity of Christ. He denied transubstantiation. He followed various odd ideas like Rosicrucianism and other ideas like that. So he was guilty of numerous theological heresies for which he was condemned by. Now, I think with Galileo's case, it wasn't the case that the church was. I don't think they felt threatened by the astronomy, because we can see that they had shown some support for heliocentrism. You know, they'd spread it around the world. They'd approved it earlier. And it's an odd thing that they would have defend Tycho's model, and Tycho was a Protestant. So why would they support a Protestant's model over a Copernican Catholic model? And I think the church was defensive, or the Inquisition for sure, was defensive against Galileo's interpretation of Scripture. And there was certainly a belief amongst theologians of the time that a scientist or astronomer shouldn't be interpreting Scripture, because that should be the domain of theologians only. And theology was considered the queen of the sciences. People would have had to study science and philosophy before they were even allowed to start studying theology. So they considered astronomers a bit of a lowly position. So did they sense a threat? I don't buy into that. I think the Inquisition was upset that Galileo had broken their court order, but I don't think they felt threatened by it.
It's more that if you understand how something works, you might even think you're bigger than God.
That's an interesting question. Like, do people? Because would people think that someone was bigger than God if we understood everything? Now, that's an interesting question. And something I'm reminded of something that Riccioli writes, and he cited directly from Scripture, saying that Solomon the wise, he asked for wisdom, and something that's written in the Scriptures that Solomon was given the gift of knowing everything about the heavens. And sure, Solomon had his downfall, right? But I don't think they would have considered that a threat in that sense. And I think people of, certainly in the early modern periods, they were quite aware of their various limits. And I don't think people thought for a moment that they could know everything about everything, because there was so much unanswered. Yeah.
Thank you very much. Any more questions? If not, then we'll break. But I'd like to thank you very much, Michal, for coming along to talk to us about this completely new subject, and wonderful subject for me anyway. I'm sure everybody really enjoyed it. So thank you very much for coming.